Hello everyone. After one short 1 week break due to a good reason, we were running SIGCOM in Coimbra, Portugal. If you missed the event, good news. Everything is already online, the proceedings, the recordings of sessions, of non-paper sessions. So I need to plug this before introducing today's seminar by Jason Livingood from Comcast, and with this very exciting topic. And I can say that everyone is looking into getting latency down from in SIGCOM, in the research community, my students, all of us as users, like when web pages, applications work smoothly. And that's precisely what Jason is going to talk about. As usual, I don't read out the large biographies of our uh, guest seminar speakers, even if they are so brief. Like Jason, you have been just putting the essence. You have done a lot of standardization products, a lot more that you have shared with us. And thanks again for contributing to this seminar. And let me stop sharing. And I am really looking to our chat conversation in 40 minutes or so from now.
Great. Thank you very much. Ready for me to start presenting?
Yes, please.
Perfect. Thank you. Well, appreciate everyone joining today. My name is Jason Livingood, and I'm from Comcast. We are based in Philadelphia and the East Coast of the United States. And we also own companies like Sky, which is an ISP brand in the UK, Ireland, and parts of Europe. And of course, NBC Universal. So we've got a lot of sports related broadcasting and other movie and television content as well. But I'm based in the wireline ISP division, and I'm going to speak today about what I like to call the decline of bandwidth and the rise of low latency. So we'll talk a little bit about that in the coming slides, and I'll be looking forward to taking questions at the end. So, how frustrated I feel sometimes. It's a great shot from an old movie, but everything that the industry, generally speaking, believes about latency and end user internet performance is pretty much wrong, or at least mostly wrong. And for many, many years, and I would say that's probably 25 years, if not more, the industry has focused on bandwidth, aka speed, as the key and most important factor for user performance. And so, the view is, well, if your internet feels slow or isn't performing well, just upgrade your speed. And that for many years was a very good proxy for end user quality. Think about going from a dial up speed of less than a megabit per second to 10 megabits per second or 100. And you can see that, things really improve. But once that initial bottleneck on bandwidth kind of goes away, it's not really the dominant performance factor anymore. And instead, what emerges is latency. And that's the thing that really affects the internet today. The problem is that really no one knows or understands what latency is, or if they do, they have a somewhat outdated definition of what latency is. So we noticed this certainly at the beginning of COVID when people suddenly shifted to working from home. And we had people with a gigabit per second of connectivity to their homes, but they still had problems with video conferencing, for example. And it was a really good indication, if they had Zoom, dropping chunks of audio or audio and video getting blocky or out of sync, or your gaming is laggy, poor voice over IP quality, these kinds of things. Those are all latency problems. They're not really bandwidth constrained anymore. They might have been back in the narrowband days of dial-up, but that's just not the case anymore. And in fact, the amusing thing about a lot of people focusing on, well, everyone needs a gigabit per second at home, even at a recent IETF meeting with more than 1,000 people attending, more than 1,000 devices using the network at peak hour, that 1,000 people only used about 860 or 70 megabits per second downstream. So there aren't a lot of things that use all of the available bandwidth that we have in the home. And so if we're having problems, there must be something else that causes it. In terms of network design and protocol design, especially around, thinking about QoS, quality of service, or diffserv, the thinking used to be that you had two attributes you had to choose from. You had to either have really high bandwidth or high throughput, or you had really low latency, but you couldn't really have both. And I think the networking world has really come around to the view over the last few years that you can actually have both. And there are things you can do to have both of those things at the same time. So let's talk about the main factor here. And I oftentimes externally like to joke that bandwidth is dead, and that we're in, as I call it, the post gigabit era. This era of after gigabits, bees to the home, and so on. And all of that is shorthand for people have hundreds of megabits per second of capacity to their home or to their phone if they're around on a 5G network, but they don't really need that, and incremental bandwidth doesn't matter that much. So from an economist standpoint, we would say that the marginal utility of additional bandwidth is declining and maybe even approaching zero. A good example here is looking at web page load times. So if you have 1 megabit per second of bandwidth and you upgrade to 2 megabits per second, you can see you substantially reduce the page load time. Unfortunately, when you get out to 8, 9, 10 megabits per second, extra bandwidth basically does nothing. So there is zero marginal utility of additional bandwidth at that level. But when you reduce latency, you can see dramatic improvements in page load time. So for example, a lot of connections these days have a working latency of about 200 milliseconds. And I'll talk a lot more about what that means. And so the result is that a page here takes about 3.5 seconds to load, 3,500. So, and that improves dramatically. That page load time improves dramatically as you reduce latency. And I'll talk, of course, about ways to reduce latency. And so, in essence, you can call it buffer bloat or lag or latency or delay, but it's really what I would say is the X factor, this unknown factor of quality of experience, or QoE. So, the first and most important thing is that when you think about latency today, which people also might describe as delay or responsiveness, Apple likes to call it network responsiveness or response time. People really think that latency is what today we would call, or I would call, idle latency. So this is like when you run a ping test on a connection when really nothing is happening on that. And what you're really testing is the distance that those packets are going and the link layer technology. So whether that's 5G or PON or DOCSIS, those are going to have different delay properties. To use an example, in a fiber to the home network using PON, you might see 5 to 7 milliseconds of idle latency. And that's based on how that optical network functions. In a DOCSIS network, because that link layer is a little bit different and we have a request grant cycle for sending packets to the network, there's higher delay because of that protocol having some differences. And so in DOCSIS, that idle latency is going to be about 15 to 17 milliseconds. So you might say, wow, 7 milliseconds versus 17 milliseconds, that sounds like a huge difference. Unfortunately, as soon as you put even just a little bit of real world traffic on that network connection, some file uploads or downloads, like you're uploading a photo to iCloud, or you're sending a text message with a photo attached, or you're starting a video call or whatever it might be, you've then gone from an idle connection to a working connection, so under normal working conditions. And suddenly that 7 milliseconds or 17 milliseconds or whatever happens to be the case can go into the hundreds of milliseconds when there's working usage of that connection. And in a lot of cases where, especially thinking of things like web pages where you have multiple round trips before a page loads, you're taking that round trip time, that delay, and you're stacking it on top of each other. So suddenly that 250 milliseconds of working latency, and 4 round trips, now you're talking about 1 full second of delay. And this is what to talk about when they so let's look at the contributors to latency slide from Nokia, who's been a real leader in the space along with us. And this is the distribution of latency. So sort of how do you explain what is contributing to the long delays? And as you can see on the left-hand side, we have propagation delay. So think of that as the speed of light over an optical cable. So if I were to go from Rio to New York City over optical fiber, that's going to be longer, and therefore there's going to be more propagation delay, more round trip delay, than if it was New York City to Philadelphia, where I am, where that's only a few hundred kilometers. So that's one thing. But even in these cases, you're only talking about 1 or 2 milliseconds of difference. You're not talking about huge amounts of difference. And there's very little that network operators can do to reduce that other than making the path shorter. And there's a famous example here of some commodities or stock traders in Chicago trying to build a straighter line connection to New York City's stock exchange, and trying to go straight through or across mountain ranges instead of around ridge lines. And they were able to shave off, I don't know, like 2 milliseconds or 3 milliseconds, and spent $1 billion to do it. So not a huge amount of return there. Then you've got the interface delay. That's that link layer that I mentioned in the last slide when talking about PON versus DOCSIS, to use one example. And Wi-Fi would be another nuclear technology. Again, not a huge difference. Okay, so I switched over to just an audio-only connection. Is that any better?
Yeah, that's coming perfect.
Okay, good. All right. Sorry, I don't know what has happened around here affecting both 5G and my wireline connection. I did hear sirens a moment ago, so maybe someone hit a pole and hooked down some power and connectivity. In any case, getting back to the dual queue standards, this technique emerged recently from the IETF as a way to solve that problem of buffering delay. And the way that we implement it in cable is we have an aggregate service flow, and within that we have a low latency queue and a classic queue. And it's important to, this is a very new concept from the IETF, and this can be done in PON, it can be done in 5G, and a whole variety of network types. But the bottom line is that both of the queues are sharing the same overall capacity. So low latency traffic isn't getting any more or less latency, and both queues have the same priority. So there's nothing there that gives something a leg up from a QoS standpoint. But the way that someone gets into it and the way that the IETF has implemented this method of improving latency is that the application developer needs to tag their traffic. So in the IP header, they need to do a marking saying, I'm asking for low latency treatment, and therefore I'm going to go into this other queue. And so next slide. Next slide, if you could, Christian. Slide 9.
I'm on 9 now.
Oh, okay, not showing it. So for dual queue, the basics is that these two queues are meant to attack that area of queuing delay that we see. And the goals are not only that there is less delay so that the round trip time is lower, but also that there's less variation in that delay. And that is important because a lot of applications can actually adapt to somewhat higher levels of latency, but it is a problem for them when it's varying all the time from very low to very high latency. It's very difficult for them to adapt to that change. So that is one of the keys of dual queue. The other thing that I did not mention was something called AQM, which is active queue management. And it is a way to implement new congestion control behavior in that classic queue that exists today. So that is another thing that helps. If you can go to slide 10, please. So one of the important things to bear in mind is that on any end-to-end link on the internet from you to some destination, there is always a bottleneck link, which simply means there's one point that has less capacity than somewhere else, and it's a place where queuing will occur. So even when you have a fiber to the home connection or other super duper high bandwidth connection, you will still have a buffer somewhere, a bottleneck link somewhere on that end-to-end path. You know, coming back to the dual queue stuff that I was talking about earlier in the presentation, I mentioned that there was always this thought to be this trade-off between low delay and high bandwidth, and that has been, you know, largely solved in part because of things like active queue management, so newer forms of congestion control, but also now because of putting two network queues called dual queue at these bottlenecks. And it was really because I think the IETF concluded that there were two traffic types, one which was sensitive to delay, like real-time conferencing or gaming, and the other that was not, like uploading something to the cloud, like to back up a photo, or downloading something like a gaming update or something like this. And because of those two fundamentally different traffic types, you should give the traffic types that are sensitive to delay some mechanism to signal that to the network and to then be able to get into a low latency queue at these bottlenecks. Generally speaking, in an ISP network, that bottleneck is going to be in the home Wi-Fi LAN and in the home CPE that connects them to the internet, and then in the ISP's aggregation router, where it brings together, you know, a group of subscribers. The last two bullets here are important from an adoption standpoint. One of the great things is that this can be incrementally deployed. So as network operators they are able to, they can deploy. Application developers can deploy one by one. And that bodes well because it allows this to be an organic growth rather than waiting for all of the benefits until everyone has deployed. So that's a big difference. And then the other, which is extremely important, is that there is loose coupling between layers. And that's one of those core internet architecture concepts where you do not want close coupling or coordination required between layer 3 and layer 7, so the IP layer and the application layer. And the reason being that coordination gets complicated, and it means that you have to do it on a network by network basis, for example, rather than just holistically for the entire global internet. So where there is loose coupling, that means development can go faster and proceed independently and everybody can sort of innovate at their layer of the stack without having to do a lot of coordination with others. So, for example, ISPs can just deploy low latency networking, and they don't have to coordinate with every application developer that is deploying it at their application level. They'll just magically work together at a protocol level without any kind of direct coordination. But the other important things, and really the only one I'm going to highlight are under the deployment principles, the first bullet, which is the notion that only applications should mark traffic, not the access networks. And there is a long history of ISPs trying to do it, including my own company, with deep packet inspection of DPI boxes. Famously, years ago, we were trying to manage BitTorrent peer-to-peer traffic, and remarking some of those packets to slow the connections down to reduce buffer bloat. And that didn't work because we had some false positives. We started marketing a collaboration app, which was called Lotus Notes, that I don't think anybody here remembers or knows, but it was a collaboration software, and that inadvertently got tagged as peer-to-peer traffic and got affected. And so we often find that when an access network tries to do this sort of intelligent inspection, that it makes mistakes. And those mistakes end up having negative effects on applications and users. But more importantly than that, because all of the traffic on the internet by and large is encrypted at this point, there is not a really easy way to identify what certain traffic flows actually are. And there are many, many equipment vendors out there that sell boxes that try to infer traffic type and then apply network policy, but they all do a fairly poor job of it. And they are slower to adapt to changes in the flow patterns compared to how quickly a developer is advancing. So never a good idea to do it in a middle box, and that's sort of part of the end-to-end argument anyway, that you don't want these middle boxes. And there's a paper on that from David Clark at MIT years ago called The Tussle in Cyberspace, about this tension between the end-to-end model and middle boxes. But I digress. Next slide, please, on slide 11. So one of the key changes with whether it's active queue management or L4S, the dual queue thing that the IETF has developed, is it is essentially trying to reduce the amount of time that it takes for a server or a sender, if you will, to notice that there's not enough capacity or that there's delay occurring and that it should slow down its rate. And so that red line, the zigzag or sawtooth pattern, that's a very classic congestion control indicator for TCP. Think of that as a control channel or a feedback loop. And it takes a while. It can take several round trips after a packet drop for a sender to adapt and slow their send rate. And when they do, they back off that send rate pretty exponentially. So they overreact in a pretty big way. And one of the objectives of things like active queue management and dual queue networking like L4S is to tighten up that control cycle, that feedback loop, and get that feedback to the sender much more quickly than it would take for a packet drop or multiple packet drops and then exponential back off. So in the case of L4S, it's actually using the ECN header, and it's adding a congestion experience marker, and applications and servers are able to adapt to that much more quickly than in the past. And as a result of that, applications have less delay. They more quickly adapt to changes in network capability and so on. Next slide, on slide 12. So there are two different options here for dual queue networking from the IETF. The first one, which was standardized a couple of years ago, is low latency, low loss, scalable throughput. So L4S. This is what we're using, for example, with NVIDIA GeForce Now Gaming and Apple's FaceTime application and so on. The other thing which is just on the cusp of being standardized, in fact, just yesterday it went to the RFC editor at the IETF to become standardized and have an RFC number issued, is NQB, so non-queue building per hop behavior. That's just a very long-winded way of saying you have very low bitrate flows that are very sensitive to delay. A good example would be DNS lookups. So very, very low bandwidth, but extremely important. You don't want any delay. Next slide. So in terms of our deployment, as of now, we've deployed to about 9 million homes. Based on the average number of devices in a home, that's about 275 million devices that are capable. And when we turned on downstream active queue management, so from our point of access aggregation to a user's home, we saw the working latency drop by half from 65 to 33 milliseconds. So that was humongous, a giant drop. And when applications like FaceTime and NVIDIA GeForce Now mark for L4S, they're actually seeing more like 18 to 20 milliseconds of delay, which is extremely close to the level of idle delay that's inherent in the network itself. So absolutely excellent performance. Next slide. So what we see here is some data from NVIDIA. And what they were seeing in the green and orange in the graph here is not only were they seeing periods where delay was spiking, but some extreme variability. So even north of 225 milliseconds of lag at one time or another during a game session. And that's extremely hard for their application to keep up with. And as soon as they turned on L4S marking, those spikes went from going up to 225 milliseconds to only 20 milliseconds. So their typical range was 18 to 20 milliseconds instead of 18 to 225. So it made a huge difference from the performance of their games and was important. Next slide. Another cloud game is the Steam platform from Valve. One of the games that we were playing during the trial was Counter-Strike, and we saw these spikes that were going in, north of 100 milliseconds, basically declined to about 40 milliseconds of delay. But so another big improvement, very similar to what NVIDIA saw. Next slide. So it is very rare that a developer like NVIDIA GeForce Now or Apple FaceTime are doing something because they control the entire software stack in their delivery, from the OS to the application. But in the case of other applications, you depend on someone else making it possible. So you can do dual queue marking both in iOS and macOS right now. It's available in the software development kit. So iOS app developers in particular are starting to take advantage of it. For Windows, we have a bunch of native apps that developers are testing, mainly Microsoft Teams is one of the big ones. In Android, it is in development, so sort of in the developer beta, as far as I understand, so a little bit behind iOS. And then for web browsers, the dominant open source behind Chrome and others is Chromium. ECM and L4S support is in development. They've actually been working on it this week to clear some of the items that are in the backlog. And then once that becomes possible, there is something called WebRTC, real-time communications. So that's a library used by the browser for things like Zoom conferences or Google Meet or other kinds of real-time apps inside the browser. So that's coming soon. And then the Nokia team has been writing a bunch of patches for Linux, and those are getting pushed into the kernel. Again, some of those even got accepted as of this morning into the kernel. So in the next Linux release, there'll be support for this as well. So all of that is great because that means that the server-side platforms in the cloud and in data centers, and then of course on the client side, in the browser, and in the mobile OS. Those support things are coming soon, and once that does, there'll be a huge wave of support or deployment, I should say, from application developers. So that's it. I think we can stop there, and I'll take questions.
Okay, great. We saved the your talk. I will start right away with one question that our research group has been arguing, because the L4S and the ECN marking depends on the end application, right?
That's right.
And what will happen if these, for instance, BitTorrent clients or other that they don't really need this low delay start using it? Uh, would that not, if every application flow is marked, would go into there for SQ? What is the strategy foreseen, or don't you see it as a risk? What is this of applications misbehaving and identifying themselves
Sure.
as?
So, so this talks about really hinting at what happens if someone misuses it. And there are two things that should solve that. One, there is queue protection, which is built into the standard. So that looks at flows as they're occurring, and if it detects a pattern of misuse, it reclassifies a flow into the classic queue. So that's one protection. But the other that I'm a bigger believer in is that there should be a very good feedback loop to the developers, because if they are a file upload and download type of an application, they actually want to build a queue to maximize the usage of the connection. And if they put it into low latency marking, they'll actually harm their own quality of experience. So they're not going to get any benefit from that. They'll actually suffer. And so I think it should actually be self-correcting.
Okay, I see. I can see one comment here of someone who appreciated the cloud gaming, the remote cloud gaming example that you brought from NVIDIA, and these delay distributions improving the experience of remote cloud gaming. This is great. And here I have another question regarding quick, right? So L4S congestion control for TCP, great in the kernel. And what about the quick outperforming TCP in many scenarios? Is there an equivalent or experimental implementation of Prague style or L4S based congestion
Yes.
control for quick? Do you
Yeah,
know?
in fact, yes. In fact, that's what Apple has been mostly using, and what some of the Google folks are planning to use for some of the things that we're working on with them at the moment as well. So it'll be available for Quick as well as TCP and UDP.
Okay, good. Let me see. Okay. Let me see here over another chat. Jason, I think we can stop earlier today. Apologies for for this, but this is also a good example of things that happen in the real internet, and when you do live seminars like we do. Again, thank you a lot for your time, for your slides, and looking forward to maybe meeting some upcoming IETF or somewhere else
Yeah,
meeting. And thanks again, and keep pushing the limits of latency and improving the
thanks.
experience of all of us.
I will. Thanks. Take care. Bye-bye.
Thank you. Bye bye.